talking about probability identities. And very shortly after our last lesson, Teacher Coco noticed that teaching dependence is going to be difficult. Okay, so we're not going to teach dependence. We're going to talk about what dependence is, but we're not actually going to teach you guys how to calculate for it. Because if you can calculate for independence, anything that is not independent will be dependent. So we only really need to know about dependence or independence in this case. All right, so let's think about who has an example. Does anybody want to give us an example? Hello, Mirula. Lovely to see you. Does anybody have an example for us of an independent event? Anybody got any ideas on an event that could possibly be independent? What y'all think? Anybody have an idea? Okay, let's do this. I'll give you guys an example. All right, let's say, for instance, I flip a coin, right? I flip a coin. Now, the one thing we need to note, guys, is that when we are talking about independent and dependent events, it's always more than one event. So it's not just one thing happening. There's going to be more than one of them, one after the other. There's always going to be more than one event. Funzo, yes, my sweetie, what's your example?
I think maybe if we flip a coin in the air and get the outcome as a head, then again we flip the coin, but this time we get the outcome as a tail. In both cases, the occurrence of both events is independent of each other.
Correct, because if before I even flip the coin the first time, Funzo, what is the probability of heads?
It's 1/2.
Correct, it's 1/2. Now that's event one. I flip my coin, that's event one. I flip my coin and I get a heads. Now, if I flip my coin again, what's the probability that I'll get tails this time?
1/2.
1/2. So did my probability change?
No.
No, it didn't, because these two events are independent of each other. We don't need the one for the other. And Funzo, you're like super smart. You deserve all the flowers. Look at you, just doing the most, doing the most. I love it, my sweetie. Thank you so much. Please, you're gonna have to put your hand up again. I want to hear Funzo's voice. I hardly ever hear Funzo's voice. I just realized. And now, Funzo, I have to talk to you the whole night. I don't know, because I hardly ever get to hear your voice. Okay. All right. So we're going to learn two formulas. If you have not written them down yet, guys, please make sure that you do. Now, the first one we're going to learn is the addition rule. And the addition rule goes with the union, or as we call it, or. If we ever see an example that has the probability and we're looking for the probability of something or something else, we're going to use this probability. Now, in the case of the product rule, which is this one over here, the product rule has the intersection. And whenever we see the word and, we're going to use that. This little star, Mara, is actually supposed to be a times. Okay, so it's going to be the product means multiply. So the probability of A multiplied by the probability of B. All right, give me a thumbs up when you've written them down. Can I keep moving? Can I keep going? I'm going to give everybody 5 seconds to write this down. 5, 4, 3, 2, 1. Let's go. Level up, level up, level up, level up, level up. I had to. It's in my blood now. All right. Okay, let's look at this next example. This first example that we've got over here. All right. It says here, a die is rolled twice. A die is rolled twice. If event A is the first roll and it shows a 6, and event B is the second roll and shows a 6 as well. My first question is, are events A and B independent? Yes or no? Are they independent? Hello, Anna. Are these two events independent, guys? Yes or no? Okay, Tiana, let me explain it like this. If I throw a dice, what is the probability of me throwing a 6? What's the probability of me throwing a 6 if I roll a die? Correct. It's 1/6, my sweetie. Good. It's 1/6. Right. Now I pick up the die and I throw it again. What's the probability of me throwing a 6 again? Correct. It's 1/6. All right. So did the probability from one event to the next one, did that change? No, it didn't. It didn't. So it's independent because the second event isn't dependent on what the first one does. I'll give you an example of a dependent event, right? Let's say, for instance, we have a bag, and this bag has three black marbles, right? And 2 red marbles. Now, what is the probability of my pulling out a red marble? Give me the probability, guys. What's the probability of me throwing a red or taking out a red marble? Correct, Namisila, good. It's 2/5 for red because there are 2 of them and there are 5 of them. Now, let's say, for instance, I put my hand in the bag and I pull out a black marble. That's gone. Remember, this is event 1, right? So in event 1, I pulled out a black marble and I put it aside. Now, event 2, this was event 1. Event 2, what is the probability of me pulling out a red marble now? What is the probability of a red marble now in the second event? Correct, Offense. Hello, Zoom user. Good. It's now 2/4. Now, my question is, remember, guys, it's not 5 anymore. It's not 5. We've taken one of them out. So there's only 4 marbles left now because we took one of the black ones out. Okay. So my question is event 2 dependent on event 1? Yes or no? Yes, correct. Because the probability of event 2 is affected by what happened in the first event. Okay. Give me a thumbs up if that makes sense. Excellent, Neo. Good stuff. Excellent. I'm glad everybody's on the same page with me. Okay. All right. Excellent. Now, let's think about this analogy. Okay. Let's think about this example that we've been given over here, where they ask us, I throw a dice 2 times. Are events A and B independent? Yes or no? Yes, they are independent because the second outcome doesn't change. The probability of the second outcome isn't changed by the probability of the first one. Right, so our answer here is yes, it is indeed. Excuse me, it is indeed independent. Now, our question says here, oh my goodness, what's going on? All right, find the probability of A and B. Okay, so now when we look at and, which rule are we using? Are we using the addition rule or the multiplication rule? I'm sorry, or the product rule? Correct, it's the intersection. So is it the product rule or is it the addition rule? Correct, it's the product rule, right? So the product rule then says the probability of A intersection with B is, oh my goodness, is equal to the probability of A multiplied by the probability of B. So I want you guys to calculate for that while I go get some water because my hiccups are getting insane. Woo.
Okay, somebody is unmuted. Please mute. Okay.
Sorry, Tiana, the union would be the addition rule, and I'm going to explain what the addition rule does, okay? We're going to get to that in just a bit. Nicely done, Asbonge, that's correct. Okay, so I know that the probability of event A was 1/6 times probability of event B, which was also 1/6. So the probability of event A and B happening one after the other is 1/36. Beautiful. Sure, Samuel, and we're only starting it next week. We're starting it on Monday. I'm so sorry, my dude.
But what about the last year's lessons?
And the last year's lessons are on there, and they're really, really good. So maybe
Okay.
go have a look on our YouTube channel, Samuel. That might help, okay? Sorry about that. Yes, Tiana.
Ma'am,
What's up? Yes.
September, yeah, I think September. Are we gonna have another boot camp, or is it just for June and December?
It's just going to be for December, my sweetie. So we're going to do it, I think it's happening in October. Okay. But we'll advertise in due time.
Yes, ma'am.
Let me just double check my emails. Let me see. Yeah, so the 21st and the 28th of October, and then November, the 4th. Okay, so it's quite late in the year, but we are going to have boot camps. All right, guys, let's put all of the stuff that we've just learned into practice. Okay. Okay, so the next example, yes, Michelle, they are. All right, the next example says here, a spinner in a game has 3 sections of equal size. So you can imagine a spinner, guys. A spinner looks like this. Okay, and they're telling us that it's been split into 3 equal parts. No worries, Yvonne, welcome. Yeah, okay. Clearly, teacher Coco can't draw, and we all know this, so no judgment. Okay, there, I split it. It's somewhat even. Okay. Oh, hi, Yusuf. No worries. Okay. All right, it says here, there's a red section, a blue section, and a green section. So there's the blue part, the blue part, the green part, the green part, and I'm just gonna color the red part in green. Okay, and the red section, there we go. Okay, so the probability of all of these will then be named as B, G, and R. Okay, now question number 1. Are these events independent? Yes or no? Namisile says yes, Funzo says yes, Anna says ye. Asbonge says yes, and I agree with you guys, because if I turn the spinner once, right, there's the tiny little spinner in the middle. There it is. So if I turn the spinner once, right, the next time I turn it, it doesn't mean it can't land on red again. It can land on red again. Okay, so we know that each of these events is going to be independent. All right, let's look at the probabilities that they want us to get. Right, it says, find the probability that when the spinner is spun twice, the following outcomes are obtained. If we spin and we get red both times. So what we want is the probability of red and then the probability of red again. Okay. What are we going to get? Now, Namisile, remember, are we adding or are we using the addition rule or are we using the multiplication rule or the product rule? Okay, be very careful, guys. Think about this. What is the probability of landing on red the first time? Let's start there. What's the probability of landing on red the first time? Good, Imelda. That's it, Funzo. 1/3. Good. Now, what is the probability of landing on red again? 1/3. Correct. So what is the probability of landing on red and then on red? Now, this is the product rule. So we're going to have 1/3 times 1/3, which should give us 1/9. Okay. Yes. Funzo, the product rule means times. Okay. Because the events are independent. Okay. Now it says, guys, what is the probability of landing on red and green in any order? So what's the probability of landing on red? That's the first time. We know that's 1/3. And what's the probability of landing on green? We know that's 1/3, correct? Now, what's the probability? Remember, they don't care about the order. What's the probability of landing on red and green, or the probability of landing on green and then red? What is the answer for both of these probabilities, guys? Tiana, I see your hand is still up, my sweetie. Do you still have another question? On Tatila,
Yeah.
be careful, my sweetie. Yes, we are
Yeah,
multiplying, not adding.
So the red one, ne? It's a
Mhm.
both times, ne? Does that now? Does both end like now mean the same thing?
Correct, because all of them have the same probability, don't they? Because they
Yeah.
cut into equal parts, right? They cut into equal sections. So we know that the probability of red is 1/3 and the probability of green is 1/3. So the probability of red and green would be 1/3 times 1/3, which is still 1/9. And again, the probability of green and then red is still going to be 1/3 times 1/3, which is still 1/9. Okay. All right. And I'm pretty sure we're onto something here. What is the probability that both are the same color? So what's the probability of red and red? What's the probability of green and green? What's the probability of blue and blue? It's still going to be 1/9. Correct. Hi, Jenna. Probability of red and red is going to be 1/9. Probability of green or green is going to be 1/9. All of them are just going to be 1/9, guys. It's not even that deep. Not at all. Yusuf, what's up? Yes,
Ma'am, I was apologizing for being late and I forgot to lower my hand. Sorry.
No, that's perfectly fine. Welcome. It's good to hear your voice. Welcome to class. All right, my boy. Okay, maybe let's change unit 23 to Yusuf teacher Nelly. Good. Okay, all right. Let's talk about mutual exclusivity very quickly before we continue. All right. So two events are considered mutually exclusive if they what? Who knows and can help us with mutual exclusivity? Who knows? Funzo. Funzo. What makes two events mutually exclusive?
I think it is when there's no intersection.
Beautiful, absolutely. When there's no intersection, when they sit like this, like that. But I want you to explain it to me mathematicalism. You know what I mean? You need to explain it, guys. The English is running out. The airtime is running out. Okay, so explain to me. We know that the intersection is going to be, let's say this is A and this is B, right? We know that the intersection of P is equal to A, intersection B must equal to what? what must be the probability of the intersection of A and B must equal to?
It will be equal to 0.
Correct. It'll be equal to 0 because there's no intersection at all. And I couldn't have put it better myself. That was beautifully put. Well done, Funzo. Excellent work. That's exactly the answer I was looking for. All right. Now, I want you guys to note that if we are talking about mutually exclusive events, the intersection is 0, but that doesn't mean that the union is 0. A union B is just going to be the probability of A, the whole of A, plus the probability of the whole of B. And now you're going to be like, Teacher Coco, isn't that just the addition rule? No, it's not. Okay, this particular one that I've written over here, I need you guys to write it down in your book, put a big nice star and thingies around it like that. This particular formula is only for mutually exclusive events. And I'm going to explain as we go. This is for only mutually exclusive events. Okay, and I'm going to explain. Now, let's say, for instance, lovely Mara, beautiful. Mara knows exactly what I'm talking about. Let's say, for instance, these two actually do intersect, right? Now, if I had to use this particular formula for the probability of A union B, this is what's going to happen. I'm going to calculate for the probability of A, the whole of A, and then I'm going to add the probability of the whole of B, right? But remember what's now happened, guys. What do we notice about this middle part over here? What do we notice about our intersection? What happened when I did that? When I did the probability of A plus the probability of B. What happened to my intersection? Correct, Namisile. Oh, lovely, good. It's calculated twice. We counted it twice. So the normal formula, the addition rule, makes up for the fact that we actually count this twice. So the addition rule is going to be the probability of A union B needs to be the probability of A plus the probability of B minus the probability of one of the intersections, A intersection B. So we can get rid of that extra one that we counted in the middle. Give me a thumbs up if this makes sense. Okay, so you'll note as we go along while I wait for my thumbs up in the chat. Okay, you'll note that in the probability of the union of A and B, where we don't include the probability of the intersection, it's because there is no intersection. So there's no need for us to count it twice. We won't count it twice. Okay. All right, peeps, let's look at a couple of examples. Let's see what this looks like. All right. So here's the question we've been given. It says, the probability of A is 0,3. The probability of B is 0,5. The probability of A or B is 0,7. And Tiana, I'm going to ask you to put your hand up, my sweetie. I don't want to lose you. Okay. All right. So this part over here is the probability of A. This over here is the probability of B. Right. Now, together, both of these things together must give us 0,7. But we already know that together they give us 0,8. So what do we know about the intersection? Tiana, where did I lose you, my sweetie?
Name.
Yes.
I thought there's no intersection. So why is our circles now like touching each other, like you say, the intersection?
Yes. Okay. In this case, we will have an intersection, but with mutual exclusivity, we don't, right? So this is all I'm saying is this is the addition rule. This is the addition rule when we have an intersection, This one over here is the addition rule for mutually exclusive events. Okay, that's the only difference. The one for intersection has an extra little bit that we have to minus.
So how do we know if
Okay.
it's mutually exclusive?
Mutually exclusive, there'll be no intersection. Okay, it's like if I had to ask you, Tiana, can you take maths and maths lit at the same time?
In some schools, yeah.
Okay, at your school, can you?
No.
No. Okay, so those two things are mutually exclusive, which means, okay, if we want to count all of these people, like all of these students, if we want to count them, right? This is the math students. This is the math students. These are the maths lit students. Now, if I want to calculate for all, what is the probability if I had to choose at random that I would choose a child who does maths or maths lit? Then I would take the probability over here plus the probability of over there. I would add them together. Okay, that's the only difference.
Is that why we subtract so we don't get the intersection if there is one?
Correct. So let's say, for instance, we're talking about English and maths and French. There'll be an intersection. So what I would then do is I would calculate the probability of this plus the probability of this minus the probability of the inside part. Because if I do the probability of both, I'm going to count the inside part twice. Okay. So I just have to minus the intersection one time. Okay. All right, I'll show you as we go along. The examples will come up. All right, yes, Namisile. Namisile, what's up?
Hey, I wanted to try the practice.
Yes, yes, let's do it. Okay, all right. So we know that the probability of A must be 0,3. That one must be 0,5. What do we know about our intersection?
We know that our intersection is X because it's not given.
All right, we can name it X, correct. Okay, so what happens to this part over here? What does that part become?
What part?
This part here. For the probability of A. If the whole of A needs to be 0,3 and the intersection is X, what do we know about A? What does it need to be?
Isn't it 0,3 minus X?
Correct, yes, 0,3 minus X. And what about the probability of B?
0,5 minus X.
Beautiful, 0,5 minus X. Now, I know that this together, the whole of probability A and the whole of probability B together is the union. Do you agree with me?
Yes.
Yes. And what is the union? How do we describe the union? And or?
Or.
Correct, it's or. And we know that or must equal to 0,7.
7.
Right. So how are we going to write this equation so we can figure out what?
Okay, I didn't write what you just wrote. I did it like using my own, I won't say method.
Okay.
But like, yeah. I said 0,7
Okay,
is equal, or I said 0,7 is equal to 0,3 plus 0,8 minus X. It's the same thing, just
minus
that
X.
I didn't do the Venn diagram.
Absolutely. Yes, it is 100%. Okay, which will give us
0,7 is equal to 1.1 minus X.
1.1.
Is it
Does
8?
it mean
Or
0,8?
it's, oh, okay, I wrote 0,5. Okay, I can see. Okay. And then 0,8.
Okay.
And then you transpose.
Correct. So we
And
get
then,
negative 0,1 is equal to negative X.
yeah, and then negative cancel each other. Yeah.
Correct. So X is equal to 0,1. Okay. I mean, we did the same thing. Same WhatsApp group. Right. So we know that this middle part over here is 0,1. This is then 0,2. This is then 0,4. Guys, just give me a thumbs up. Okay. if you're understanding what's happening. Is everybody okay with what Namisile has done here? Beautiful. Excellent stuff. Now, I need you guys to remember that the probability of all events in one sample space need to equal how much? How much do all of the probabilities need to equal to when we add them all up together? Sure, Funzo, you're on fire today. That's it, Atlechang, good, Namisile. But at the moment, guys, we only have 0.7. We've only got 0.7. Where does the rest of it go? What do we do with the rest of it? Outside, correct, is the complement. Good. So we know that the other 0.3 needs to go into our rectangle. It's not part of our circles. All right, okay, let's get to the questions. I want you guys to answer these questions A, B, C, and D on your own. When you're done, you know the drill, peeps. Pop your favorite emoji in the chat. Okay, go for it. Yes, yes, Yvonne. Hi, Funzo.
Hi, ma'am.
Hi, my sweetie, what's up?
I was asking if I could answer the questions.
Yes, 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 absolutely. Okay, I'm going to ask you to mute for a little bit. We're going to give everybody else 1 more minute and then we'll get started. Okay.
Okay.
All right, just pop your favorite emoji in the chat for me while you're waiting. Yeah. Love that attitude, Samuel. That's exactly what we love you. Hi, Danvir. We didn't even hear you come in. You were just like so sneaky, just like came in the back, didn't say nothing, just came in and was like shh in the background. Don't know how I feel about it. Oh, no worries, Denver. It's perfectly fine. It's perfectly fine. We're just happy you're here. All right, guys, let's get started on these questions before we run out of time. All right, Funzo, let's talk about the first one. Okay, so the first question says here, that we want to find the probability of A and B, and we know that's going to be where? It's the what?
intersection.
Correct. So what is the intersection?
It's 0,1.
Beautiful. Good. 0,1. Nicely done. All right. So let's talk about the probability of not A. What would the probability of not A be?
So we will say 0,4 plus 0,3.
Beautiful. 0,4 and 0,3 together will give us 0,
It will give us
7.
0,7.
Beautifully done. All right. So the next one says, what is the probability of not A and B?
It's
What is that?
0,2. 0,2 plus 0,4 plus 0,3.
Correct. Beautiful. So we know we're just going to take everything that's not part of and put it together. Oh, Funzo, here's what we can do. We know that the full probability is 1. So I can just go 1 minus the not. Okay. And that's going to give me the same answer. I'm also going to get 0,9. You see that?
Yeah.
So you can do it that way. We can either go 0,2 plus 0,4 plus 0,3, or we can just say 1 minus the not. And then we'll still get to the same answer. Okay. All right. And then the probability of not A or not B. What does that leave us with?
0,3.
Beautiful. And I mean, just all the flowers from the, as always, because you just like, you crushed that. We finished that in less than a minute. You were just like, boom, 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 boom. I love it. Beautifully done. Sure. Guys, some of y'all, guys, be like Funzo. Be like Funzo. Be like Funzo. That's all I'm gonna say. That's how we're gonna end. That's how we're gonna end it today. Okay. Be like Funzo. That's the slogan for today. All right, let's look at our next example. I wanna be really quiet, and I want you guys to try and figure this one out for yourselves. Now, read the whole question. Okay. The positive vibes in the chat are taking me right now. Yes, thanks, Teacher Nels. I love it. All right, I need you guys to read the question for yourselves and think about this, guys. We are looking at 2 different events. Okay, one happens on a specific day, the other one happens on another, or the 2 events are happening one after the other. All right, so we're looking at dependence and independence. So read very carefully. Once you're done reading, once you've read through the entire question, I want you to pop the nerdy guy with the glasses in the chat. Read through it, make sure you understand it. Once you've read it and know that you understand it, then we can have a conversation. Okay. I mean, take your time, but I mean, let's not be here for the next 15 minutes reading one question. Teacher Nels, I feel like you're judging me right now. I feel so judged. Sorry, this should read chance. I don't know why it says 0,11 change. It should say 0,11 chance of winning both the art and the talent competition. Yes, tell her, Samuel, tell her. Correct. The intercept. It's Denver, it's not the intercept, it's the intersection. The intercept is that thing that the straight line graph that your parabolas and your hyperbolas and your straight line graphs cut on the x and the y axis. It's the intersection, yes. It's okay. It's okay. Yes, Tiana, that's it. We're talking about the 0.11. Okay, lovely guys. Okay, that's all the time I'm going to give you guys to read through this. Now, let us do what we should do in this case and just draw this into a Venn diagram so we don't have issues where we are kind of like stuck and we don't know what we're doing with what, right? So we've got two events, right? Now, one of them is an art competition, right? So we're going to name A for art, and over here we're going to say T for talent competition, right? Then we know that, let me just move this a little bit closer. Don't like how far you are. There we go. Feel the love. There we go. All right. So we are told that the probability of winning the art competition is 0.19. The probability of winning the talent competition is 0.13. But now, suppose he has a chance of winning both the art and the talent competition at 0.11. Now, that 0.11 is in fact the intersection, so 0.11. Now, what do we have left over here and over here, peeps? How much do we have for A? Just the art competition alone. How much are we going to get? Correct as Bonge. That's it. Ontatile, beautiful. Namisile, check the number of zeros you have there. Okay, it should be 0.08. Okay, be very careful. Danvir, 100% correct. That's exactly what we're looking for. Good. And on the other side, we're going to get 0.02. That's it. 0.02. Okay, cool. But like we said, guys, the probability of anything altogether must equal correct, Untatile, that's it. It must equal 1, correct. So we need to add up all of these probabilities, and whatever's left over goes outside of our circles. So 0.08 plus 0.11 plus 0.02 would give us how much? It gives us 0.21. So what goes on the outside of our circle? .79. All right, Yvonne, all the probabilities of anything put together must give us 1. Okay, so if we think about the probability of heads, the probability of heads is 1/2, and the probability of tails is also 1/2. Together, the probability of heads and of tails must give us 1. So the probability of any event happening in any order must equal 1. Okay. I hope that makes sense. All right, let's look at the first one. It says, define the events when the boy wins the art competition. The probability of A. What is the probability of A? Asi, remember all of them must equal 1. So we didn't know how much this last one on the outside is. So we're going to go 0.08 plus 0.11 plus 0.02 plus x must equal 1. And then solve for 1. Oh, it's Oratile. Oh, sorry. Okay, we're going to change your name. We're going to change for you now, your name for you now, Oratile. I feel like maybe you're using mom's thing. Okay. All right. So, guys, what is the probability of him winning the art competition? Now, be very careful before you say whatever answer you are thinking of. Okay, we must consider the whole of A. What is the probability of the whole of A? Correct, Namisile. That's it. Yes, Danvir, good. We're going to add them together. So that must give us 0.19. What is the probability of T? The probability of him winning the talent competition? Correct, 0.13 or 0.13. Okay, what is the probability of A and T? Remember, and is the intersection. This is the intersection. What is the probability of A and T? Correct, 0.11. Okay, now let's look at this next question. It says here, are events A and T defined in A mutually exclusive? Yes or no? Are they mutually exclusive? Funzo says no, everybody else is quiet. I'm not 100% sure where we are at. Okay, I'm seeing a lot of no's. I need somebody to put their hand up and tell me why they say no. Anyone but Funzo? Funzo, I don't want to pick on you right now. I need somebody else to answer one of these questions. Can I hear somebody else's lovely voice for a change? Namisile. Okay, Funzo, you got the next one. You got the next one. Namisile, why do we say that the events are not mutually exclusive?
Okay, because number one, the circles have an intersection, and for it to be a mutually exclusive circle, they're not supposed, they're not supposed to have an intersection.
Correct. But what does this actually tell us? What does the intersection actually tell us?
That it's not a mutually exclusive.
Yes, but if we look at the idea of the example they've given us, right? It says he has a 0.9 probability of winning the art competition and a 0.13 probability of winning the talent competition. What does the 0.11 represent exactly? Like what Janvir is saying in the, he's a very smart somebody. Look in the chat.
Thank you, Denvier. Wow, there's a possibility of winning both events.
Yes, absolutely. Just because he wins one doesn't mean he can't win the other one. He can win both. Yes. And that is what the intersection in the middle means. You see that?
Okay, thank you, Denvier.
Okay. He's busy in the chat. You're welcome, Queen. We got you. You got you. Tiana, what's up, my sweetie?
Ma'am, so
yes,
thereby are events A and T defined a mutually exclusive. Like, it's the same question. Like, why are they mutually exclusive? Is it because it's a decimals and stuff? Is it because it's gonna equal to 1, or is it just because I see intersection? I'm like confused.
Okay, so remember, mutually exclusive events are two things that can't happen at the same time, right? So yes. Can this boy win the art competition and the talent competition?
No. Oh, I see. Oh, thank you, ma'am.
Yes, he can. Yes, he can win, right? He can win both.
Both of them. What if they're not on the same time?
Yes.
Like, okay, what if they are on the same time?
But what if his talent is painting?
Oh.
What if he goes on stage and then he starts like painting someone in the audience? He can win both, the art competition and the talent competition. Okay, so they're not mutually exclusive because they can both happen at the same time. Okay. Okay, keep putting your hand up if you're still confused, Tiana. I don't want to leave you behind, my sweetie. Jasmine. Okay, all right. Okay, it says here, what is the probability that a boy does not win the competition? What is the probability of not, guys? of winning the art competition. The probability of not art or art complement. What would the complement of art be, guys? Correct, Danveer, but you must add them together. Don't just say that, we must add them together. Right, so what are we going to get? Okay, we're going to get 0.02 plus 0.09, and that should give us 0.81. Okay, that's the probability. Okay, now I want you guys to look at this next example that they've given us here. Okay, they are saying, what is the probability that he wins the art competition or the talent competition? Which rule are we using, guys? The product rule or the addition rule? Correct, the addition rule. But I want us to be very careful, guys. Okay, when we are saying we're using the product, the addition rule, right? If we're going to look for the probability of or, we're just going to take this and that and that and add it all together. Okay, we're going to add all of them together. We're going to go 0,08 plus 0,11 plus 0,02, and that's going to give us 0,21. Right. Now, if I had to use the addition rule, I would use these numbers up here. I would use 19 and 13 and the intersection. And I'll show you what I mean by that. So the probability of winning the art competition or the talent competition, right, is going to be 0,19 plus 0,13 minus the intersection 0,11. And if you add all of those up together, they will also give you 0,21. Okay. All right. Give me a thumbs up, peeps, if we're okay with the exercise we've just done.